by David Buckley from the South African Astronomical Observatory. So David's, of course, been involved with the Southern African Large Telescope project for a long time at SAAO, and he's now leading, for the last several years, has been leading this large follow-up program looking at transients with SALT, which he's going to be telling us about today. Over to you, David.
Great, thanks very much, Matt. And it's great to be talking to people here about the work that we've been doing with SALT on transients. As Matt says, this is a program which initially was the first so-called large science program, but there's been now others. In fact, I think you're leading one, Matt, as well, a large science program on SALT. Transients and time domain astronomy is something which is a new frontier. It covers, by definition, anything that changes. So, if you like, things that go bump in the night. And with our sort of international global network of telescopes these days and the instrumentation that we have on these telescopes, we're able to look at things that vary on a wide range of timescales, from the smallest to milliseconds or even microseconds to obviously longer periods to decades even. Transient objects vary over all of these different timescales. They cover a huge range of different types of objects, from the nearest solar system objects, for example, like comets and asteroids, to the most distant objects, the most energetic objects in the universe. And these two little pictures here show on the left the artist's impression of the major event of the merging neutron star kilonova that produced the first optical or electromagnetic counterpart of the gravitational wave source, GW 170817. And that was a highly energetic event, not that distant. It was in the local universe. The one on the right is just an example of a comet that was discovered by one of the transient detection telescopes at Sutherland called MASTER, that I'll talk about. Transient discoveries have really boomed in the last decade or so. This is because of a number of international facilities which are discovering transients, either because they were designed to do so. For example, the Assassin, the Zwicky Transient Factory. These were two ground-based telescope systems that are designed to look for transients. But other telescopes and other missions, like, for example, Gaia, that we're all familiar with, that's mapping the whole of the Milky Way, it's finding transients as a byproduct. And so we make use of the fact that all of these different observatories make rapid alerts on discovery of transients. And then, of course, the real work begins with ground-based and space-based facilities to study what they actually are. And so in South Africa, we began, I guess, in 2015, but it really took off the following year, a program to basically follow up on transient discoveries, and particularly things that might be of interest to the community that is here working on such objects. So in my own case, it represented people who are working on cataclysmic variables, but also X-ray binaries. And it's grown now into a much bigger program, which involves basically all different types of transient classes. And so what we've been doing with SALT is in some way in preparation for the next big step in transient astronomy, which will be heralded in by the Rubin Observatory's Large Survey of Space and Time, LSST. Some of you might remember it. It used to be called a Large Synoptic Survey Telescope, but it was renamed last year. So at the moment, with the sort of follow-up that we've been doing, say, with SALT since 2016, and indeed other projects around the world doing follow-up, it's been a sort of manageable exercise, notwithstanding maybe the ZTF, which is a facility that is producing hundreds of thousands of transient alerts. But up till now, we've been doing it in a fairly ad hoc manner, following up on transients in a fairly manual process. But of course, with the Rubin Observatory and the prediction of discovering 1 million transients a night, or variable or transient objects a night, we can't obviously use these sort of outdated tools. We need to learn from what our experiences are, doing it in this manual process, and use that as training sets for machine learning techniques. So the work that we've been doing in Sutherland with SALT, and actually some of the smaller telescopes are used for follow-up as well, has been using all of these alerts from the globe, but also now 2 telescopes which are operating actually at the Sutherland site. The first one started in 2015, and it's one of a network of Russian telescopes. It's only one of 2 that operate in the Southern Hemisphere. And it's a wide field optical telescope that surveys the whole of the sky, continuously looking for transients, and actually also following up on transient discoveries, particularly GRBs. And I'll talk about that later. So it has quite a good record of being on a target, on a GRB, 22 seconds after the alert came in from the SWIFT spacecraft, for example. And then more recently at Sutherland, we have MeerKAT, which is the telescope which is looking for optical counterparts of radio transients. So it works hand in hand with MeerKAT to look in the same fields that MeerKAT is observing in case a radio transient is discovered, and there'll be therefore a simultaneous optical image. So this is where the alerts come from. And then the program itself, I'll just briefly summarize. It's grown into be quite a large allocation in each semester, typically now up to 300 kiloseconds. And it has a large fraction in the highest priority, what's called P0, the high priority class, because of the fact that a lot of these need target of opportunity override to get immediate results. And so the program, as I say, has been running since 2016. It's been extended now. It's coming to an end at the end of October this year, but it's expected that we will reapply, remotivate with a new proposal, and hopefully that would be approved and we would continue for the next 3 years. It's a multi-institutional, multi-partner program. Currently, there are 5 South African institutions involved. It's open to anyone who has an interest in transient work. So I would encourage anyone who are not at those institutions, including at UKZN, if this is something of interest, then you're more than welcome to join. There are 4 SALT partners involved. In total, at the moment, we have 36. In fact, I think that could be out of date, a little bit more than that. Co-investigators and a number of including a number of graduate students. And we've also been involved in collaborating informally with groups outside of the SALT partnership, namely in China and Russia, and more recently Germany and Namibia. Some of these through bilateral science agreements, for example, with the China-Russia collaboration. So here's a picture of SALT, and this is just sort of quite a nice thing that shows the enormity of the primary mirror. And that just tells you this is a big telescope and it has a really good light gathering power. That means you can look faint or you can look at short period phenomena because you can run your instruments to look at short period variations when you've got a lot of photons being detected. The downside is that the telescope doesn't point anywhere in the sky at any one time. It has this footprint, which is shown here in the declination hour angle plot, where you can only observe within that annulus. Nonetheless, in any given night, most of the sky is covered. Something like 70% of the visible sky that during the night passes through the SALT viewing window. So with a telescope like SALT, which is 100% Q scheduled and done through service observing, so the astronomers don't go up and use it, we can populate the queue with proposals and targets and blocks, and they will get observed automatically, and how soon they get observed depends on the priority, which is a dynamic thing. So although the telescope is restrictive in its pointing, it's ideal because of the Q scheduled nature and the fact that we can do targets of opportunity. So it is a good telescope to do transient astronomy with. And the other nice thing about it is all of the main instruments, all three facility instruments, which are just shown here, the Robert Stovey spectrograph, which is the workhorse instrument of the telescope, Salticam, which is a fast imaging camera, and the fiber-fed high-resolution spectrograph. All of those are immediately available at a flip of a switch, or not a switch, but a mouse button click. You can change from one instrument to the other in a matter of 30 seconds. So you can be very flexible in the way you observe and sort of choose what is the best mode for the appropriate observation. So the program, as I said, covers a wide range of different transient object classes. And we've often seen this diagram at the top right, which is a time-scale luminosity diagram showing where transients lie in terms of those two parameters. And we've often seen this in terms of a so-called Zwicky diagram, which has basically similar sort of presentation. This was one produced by my colleague Jeff Cookie in Swinburne Institute, who works on transients as well. And it just includes some of the more recent interesting things which people are starting to look at, which weren't in the previous diagrams. But these are basically covering all different types of transient classes. And in terms of the SALT program, the ones listed here are all the ones that we have been looking at. And I'm going to show some results from some of these, but I'm by no means expert on all of these classes. These are things which are being done led by other members of the collaboration. So for example, the things to do with tidal disruption events, transients in other galaxies and supernovae and something, and so on. These are all things which I'm certainly not expert on, but we have done some nice science with them. And the ones highlighted in red are some of the recent results that have been leveraged by, particularly in the case of gravitational wave and neutrino events, by new multi-messenger facilities. For example, advanced LIGO Virgo and Antares and IceCube for the neutrinos. And then, of course, we mustn't forget MeerKAT, which has been operating for 2 years now, nearly 3 years, which also has a transient program called ThunderCAT. And so in the last 2 years, we've started to do coordinated optical radio observations of transients as well. So I'm going to show just a few examples of things that we've done. And this is one example of highly energetic objects, flaring blazars, which are an interest of the group at the Free State and Northwest University, where they are reacting to alerts from, for example, Fermi or Swift of changing states of blazars. And in particular, what we've been doing with SALT is to monitor these systems in the flaring state and in the quiescent state spectropolarimetrically. So this plot here shows a normal spectrum at the top, but in quiescence in blue and in outburst or flaring state in red. But the main thing to take away from this diagram is the polarization measurements, which are these values here, the linear polarization reaching up to 8% during the flare, compared to only down at maybe 5% at quiescence. But the thing of interest to Marcus Butcher and Brian van Solen and others is the change in the position angle of the linear polarization, which tells you something about the changing geometry of the jet during the flaring state. And so this is some work which that group have been doing very successfully, coordinating it with multi-wavelength observations. Sticking with gamma rays and so on, this is a rare example of a successful SALT observation of a gamma ray burst. So gamma ray bursts are typically fast, and they typically also don't get to be very bright optically. Therefore, you have to be very quick, typically within an hour, to get a useful observation, because more than that, and the object has faded to obscurity typically. This is a counterexample of one that was observed in December 2019, which reached 10th magnitude, so a rare, bright, and long GRB. And the nice thing about it was detected by the MASTER optical transient detection telescope at Sutherland, and this light curve here shows the initial points, which you can see were taken only a matter of 30 or 40 seconds after the announcement from the gamma ray satellite. And so these are the data points from a wide field camera on the master mount, then more intensive with the main telescopes here. This is South African data in the blue, and then it's taken over by data in Argentina, and then this is archival data in the green. So you can see that the decline in brightness from 10th down to, well, eventually it petered out way down here. But when we got onto it with SALT, it was still at 16th magnitude. And so we managed to do spectropolarimetry, which is a rare thing for a GRB, with SALT, and our colleagues in Chile managed to get onto it with the VLT at this time, around about here. The SALT observations were around about here, where it started to plateau out. And so we detected a polarization of about 1.5%, relatively low. And the conclusion is that this is consistent with a forward shock in a normal GRB, not a reverse shock, and a refreshing of the shock that causes a sort of halt in the decline and even a slight brightening during this phase. So on the basis of the successful result, we applied to get radio observations with MeerKAT. I should say it was detected by the ATCA telescope in Australia at the time of the outburst, but we motivated because often the radio brightness stays fairly bright for a month after the outburst. So we were successful in getting a DDT observation, and here is the picture of the MeerKAT image showing the detection of the GRB about a month after the outburst. Still sticking with the high energy, one of the programs that's been very successful with SALT is the follow-up of NOVI. And this is a program that started off being led actually by a PhD student here. He's now a postdoc in the US, but this work has shown the real ability for SALT to do synoptic observations of novae during their outbursts. And on the right is a montage of different spectral lines taken at different dates during an outburst, showing the evolution of the lines, which is what we can do with SALT, with this high resolution spectrograph. We can look at the changing profiles which tell us something about the dynamics of the nova outburst. But in the case of this particular object, which is called V906 Carina, this happened to be in the field of view of a small nanosat called BRIGHT. It's a constellation, I think 3 of them, which is looking at very bright stars to look at oscillations. And the nice thing about it is that it observes continuously without any interruptions. And so over a period of about 40 days, this nova was continuously being monitored by the BRIGHT optical satellite. And you can see there the light curve and a number of different sort of peaks, very different to the canonical light curve of a nova. But the really interesting thing was that Fermi also observed it and also observed peaks in the gamma rays coincident with the optical peaks. And this led to the idea that the outbursts are far different from the normal nova paradigm, and that the gamma rays come from shocks that are created in the ejector. So this is all new stuff that's being done, and SALT is contributing to this, this science. This is some examples from our Polish collaborators who work on a telescope called OGLE in Chile, which is looking at variables and transients. And in particular, they're interested in nuclear transients in other galaxies and things called tidal disruption events, which are thought to be the disruption of a star as it passes close to the supermassive black hole in the center of the galaxy. And these have predicted light curves, achromatic light curves, and changes in spectral line behavior. And so this is an example of one such object, which is not clear that it really is a TDE, that it might actually be consistent with other type of transient. But nonetheless, this is an example that shows how you can combine information from different telescopes. You can see the SALT spectrum here, and other telescopes contributed to the spectra here as well. So this is an example of some of the work done by our other colleagues. And this is another one which is similar to these similar to the previous study. These are all observations taken of this transient system, an assassin discovered system, which again, it's not clear whether it's a variable AGN or a tidal disruption event. But again, it's representative of a multi-wavelength study where the SALT spectra are quite important in interpretation of the data. Here's a sort of artist's impression of what a TDE is all about. Here's a supermassive black hole, and as the star approaches, it starts to get tidally disrupted or completely disintegrates, and you get an increase in the brightness in the central regions of the galaxy due to this ripping apart of the star. And I'm showing this particular observation because it is the first time that a TD has had polarimetric observations made of it, or successful spectropolarimetric observations, again with SALT showing about a 2% level of linear polarization in this particular event. So TDEs were predicted about 3 decades ago, but they've only really started to be found in bigger numbers with X-ray surveys and optical surveys. But they're very important in the sense that they're able to probe the supermassive black holes and the nature of the stellar dynamics and the nuclei of galaxies. Things we know all about with our own Milky Way, of course, from the wonderful adaptive optics work done of Sagittarius A star, where you can actually see the orbits of the stars at the center of our galaxy, and possibly flare events associated with minor tidal disruption events, perhaps. I'm going to talk a bit now on X-ray binaries, and this is more close to what I work on. So we look at both high and low mass X-ray binaries, and the thing that determines how you classify them is really the high and low comes from the companion star, not from the compact accretor, which can be a neutron star or a black hole. So this is a sort of standard cartoon for any sort of X-ray binary system, whether it's a black hole in the center or a neutron star in the center. And so there's contributions to the luminosity of the system from different components at different wavelengths. You see a strong accretion disk at some points when the mass transfer rate is high. When it switches off, the accretion disk becomes very faint, and that's when you can start to see the secondary, which is typically just well below the luminosity of all the other components. And they go through these instabilities and transitions from what we call hard states to soft states. And during that transition can launch a jet, which can be detected in radio, for example. So The high mass X-ray binaries are, as I say, that it's the companion which determines whether it's called high or low. So these are typically B-type stars, either dwarfs or giant stars. They're typically in wider orbits in the lower mass X-ray binaries. And these are some examples of SALT spectra taken of a system which has an eccentric orbit where the neutron star accretes every time it passes through this equatorial disk, which is being shed by the rapidly spinning BE star. So this is called a type 1 outburst when it moves through this disk every periastron passage. When it does that, it forms its own little accretion disk around the neutron star, which dissipates at some point. And so there's been a lot of work done on systems observed with SALT, particularly ones in the Magellanic Clouds, which has quite an overpopulation of these types of high mass X-ray binaries. So on the one hand, we get the spectra from SALT. On the other, we have both optical observations as well from other telescopes, like photometric observations from the Ogle telescope that measures its I-band magnitude, which is in blue here, correlated with the equivalent width of the emission lines, which tells you something about the status of this disk surrounding the BE star. These are other examples. I don't have time to really dwell on these too much, but most of these high mass X-ray binaries which are found in the Magellanic Clouds are simultaneously X-ray pulsars, because the neutron stars are spinning fairly rapidly, and so they are seen as pulsing systems in the X-rays. So we've observed a couple of these, and this is one that Utemelang Monageng, who was a student, is now on the staff at UCT and SAAO. The name is SXP, means Small Magellanic Cloud X-ray pulsar, and the number is the spin period, 91 seconds for this one, 4.78 seconds for this. So a lot of the work that we've been doing is coordinating between X-ray observations, particularly with the SWIFT X-ray satellite, and getting regular synoptic observations in the optical with spectra from SALT shown here, and from the Ogle telescope, light curves shown here. This is an example of a low mass X-ray binary with a potential black hole accretor. And so this was discovered as an outbursting transient back in 2014. And it's had a number of eruptions since, and the latter two have been observed by SALT in 2017 and 2019. It's thought to have a black hole more than 9.3 solar masses from a dynamical solution of the radial velocities. But the interesting thing, which was the first time this has been seen, are these sort of dips in the light curves. So if it was non-varying, it would just be flat. And you can see these sort of dips. And this is taken during the outburst from April through to July. And what you might notice is the dips seem to come further and further apart as you progress. And so that's exactly what's happening. The dip frequency is changing during the outburst. And the interpretation of this has led to a model involving the fact that the source in the center is mostly obscured by the outer region of the disk, by the inner region of the disk, in particular by vertical sort of extents in the disk, which, because this is being rotating at the Keplerian period of a few hundred seconds, causes these dips that come and go and increase in period, because this is propagating outwards in the disk, this sort of vertical extent of obscuring material. So that was published in a paper in 2019, just based on the photometry that we did with SALT. But it then was followed up by spectroscopy. And what we noticed was not only does it show dips in the continuum, but it shows absorption line dips in the Balmer, and in particular helium-2, which is a totally new discovery of finding helium-2 absorption in a low-mass X-ray binary. And so this just shows the sort of averaged absorption lines during these dip periods, and you'll notice that they're systematically offset from zero velocity. So these are blue shifted lines coming from what we think is an expanding blue shifting hot disk wind coming out from the central regions of the binary. And models were compared with the data, and only for very high X-ray luminosities, much higher than previously thought, could we match the data to the models. And that's showing that the system is a much more luminous X-ray source than thought. And the reason why we don't see it as a massively luminous system is it's mostly obscured by this inner disk. I'm going to skip these because this is just further observations. So then there was another observation of a source in the Magellanic Cloud, which was so-called Supersoft Source. And so these are systems which show most of their luminosity below 1 keV, and they're typically thermal pseudo-black bodies. In the case of this system, something with a 900,000 degree temperature. And it was interpreted from the observations as an outburst due to what we call a spreading layer on the surface of the white dwarf, which is the boundary between the accretion disk and the white dwarf. Quite different to other supersoft sources that involve thermonuclear events on the surface of a white dwarf. I'm just going to rush through these because I'm aware that I'm running out of time. I'm supposed to finish in 5 minutes, but I might skip this. This is just a interesting ThunderCat result. So this was the first radio transient, which was found to be a 21-day binary, and therefore an active, probably an active, highly spotted star, RS-CAN-VEN system, where SALT produced a nice radial velocity curve. And in the original paper, we claimed it was a 21-day, 0.25-day period, but later observations have refined the radial velocity, and there's a definite difference between the spectroscopic and photometric period, which is an indicator of asynchronous rotation. I'm going to move on to results that have just happened in the last 12 months, and this has come from collaboration with eROSITA. This is the new German instrument on the Spekcrum Röntgen-Gamma satellite, which has two major instruments, one of them being eROSITA. And this is a beautiful image, X-ray image of the sky taken in the first sky survey. So eROSITA is scanning the sky continuously and building up this wonderful image and detecting variable and transient objects. And perhaps the most amazing discovery is the discovery of two so-called quasi-periodic eruptions from the center of two normal galaxies. So you can see here these light curves showing these quasi-periodic eruptions over a few hours in two different objects, which have been interpreted as due to the rotation of a black hole around the supermassive black hole at the center of the galaxy. These are only the third and fourth quasi-periodic eruptions ever detected. The previous two were found in AGN galaxies. And so they're most likely due, or thought to be then, due to the normal accretion disk instability that you have for a radiation pressure driven accretion disk instabilities. But in these systems, the SALT data have shown that they are normal galaxies. This is a typical spectrum here showing the galaxy with fairly narrow emission lines, certainly not an AGN. And so this is about to appear in Nature. It should be out in the next couple of weeks. And the really interesting thing is that these are not AGN galaxies. And so the idea that you can explain it by an orbiting black hole of less than 10 to the 4 solar masses around a supermassive black hole has major implications for example, gravitational wave and in-spirals and the electromagnetic counterparts to those sort of events. eROSITA has also been looking at how X-ray variability changes and the accretion state changes in so-called changing look galaxies, changing look AGN, I should say. And so we've observed now 30 such systems which show variations between one epoch and another, some taken with SALT, some with other instruments, showing that changing look is actually far more ubiquitous than maybe previously thought. I've already shown this TDE, so I'm going to move on. This is a tidal disruption event, which I mentioned earlier. So again, eROSITA has found some examples of those, and SALT again has been taking spectra of these TDE events. And then so far we've observed 4 of them, and these are the spectra of those 4 TDEs. Finally, I'm going to talk about some things that are more of my own interest, which is a compact binary system. This is another eROSITA source, which is actually discovered to be a majorly bright object at 12.5 magnitude, previously unknown. And it looks very like, well, it is a cataclysmic variable, we're quite sure of it, but there's some indications that it might be magnetic. And we've been doing a lot of follow-up, even with the smaller telescopes, on this particular system. And then finally, with eROSITA, we've also been observing, again, new discoveries in the Magellanic Clouds. So this is work that the BE X-ray binary people working in the program, for example, Itu Monaghan, Vanessa McBride, Lee Townsend, have all been working together with some of our UK colleagues on new discoveries of BE X-ray binaries. And these are just some examples. I'm going to skip on and move to the last part of my talk, which is the future. So you've seen what are, admittedly just examples. There's a lot more I could talk about, but there's just no time to do that. But there's plans afoot now to expand the way in which we do transient follow-up, particularly in the era of the Rubin Observatory. And so a program has started just in the last year to create what's called an intelligence observatory. And this is just a nice photo of all of the masses of telescopes up at Sutherland now. Many of them are robotic already. Some of them are remotely observed, can be used in remote observing operations. And the idea is that we will try to create a network where we can automatically trigger observations from transient alerts. And so what this would involve would be getting, for example, transient alert brokers that are able to send alert notices, and then for, depending on the information available about the alert, like its brightness or how it's changed in brightness over time, then software which can then be used to remotely configure and then observe these objects would then automatically take observations of an appropriate nature with an appropriate telescope. So this is all, as I say, in support of this, this is a picture of the Rubin Observatory being built in Chile. It's an 8.4 meter telescope with an enormous field of view, almost a 10 square degree field of view, and the biggest camera ever built in astronomy, a 3.2 gigapixel camera, which will take observations of somewhere between 15 and 30 seconds, depends on what sort of cadence people want, what they decide on. And it will do a whole survey for 10 years of the whole southern sky. And during that time, it's going to be finding millions of transients. And so South Africa is now thankfully involved in this project. It has been for a couple of years, and there are 3 current PI affiliates, South African PI affiliates, of which Matt there is one, Michelle Lochner is the second, and I'm the third. And we all have different science interests, and of course mine is transient science. So you'll probably seen that in fact South Africa's involvement in this has stepped up because of support for our in-kind contribution to the LSST follow-up by offering various facilities to do follow-up with, like with SALT and with the smaller SAO telescopes. In the case of Matt, it's also MeerKAT data. In the case of Michelle, it's software to do with machine learning and so on. So in the future, we expect to at least double or triple the number of different groups, PI affiliate groups within South Africa. So there's a lot of opportunity going forward. And I'm just going to finish with the next big thing, the next future, and that is a project which is just getting off the ground now after an initial proposal in 2018 and an acceptance in 2019 and working towards a full proposal. And this is something which is called the BRICS Intelligent Telescope and Data Network. And so this project involves 2 things. It involves both a big data and big compute component, which Russ Taylor is leading, and it involves a transient component, which I'm leading. And the idea from the transient side of things is that just like we are networking our own telescopes in South Africa to do intelligent transient follow-up, we would wish to do this using all of the facilities within the BRICS countries. Not only that, we have an ambitious goal, if I go back to the previous slide, of developing a global network of small telescopes, 1 meter telescopes, 72 of them deployed in longitude and latitude, covering the whole globe, each of them having a 25 square degree field of view. Why would we do this? It would give us 4 pi steradians coverage, in other words, the whole sky being observed with a cadence of about less than an hour. This would be a whole new frontier, opening of a whole new frontier in terms of cadence of rapidly varying objects. And you know, we've talked about LSST, but its cadence is typically 3 days, not 1 hour. And also, of course, it's not covering the whole sky simultaneously. So this would not go as deep as LSST, but it would cover the whole sky and would still find many new and interesting, compelling objects. So this project, as I say, has just started. The Department of Science and Innovation have given initial seed funding of 3.5 million rands to get this off the ground, and we're expecting similar amounts to come from our BRICS partners over the coming year or 2. And furthermore, for the massive sort of phase 2 of this, which is building this network of 1 meter telescopes, this is already a project which the Chinese are considering, called Citian, and the Russians in a smaller case with something called Phobos. And so it's very synergistic with existing planned projects in those BRICS countries. So although the price tag for this is a hefty 300 million euros to build this telescope network of new telescopes, it's still something tractable, particularly if the Chinese decide to adopt it as a new infrastructure project, astronomy infrastructure project going forward. And with that, that brings me to the end of my talk.
Yes, hi David. Yeah, I always enjoy your talks. Yes. Just something of a general question I've often wondered about, given that there are so many transient alerts and so many things you possibly could decide to observe, how do you people actually on a night-by-night basis decide, oh, this is what we're going to do? Are there
That's a
Is there
very
somebody-
good question. That's a very good question, Hartman. Sometimes it's who shouts loudest, who's most proactive. So, for example, we had the NOVA program going for a while, and nothing happened until Elias Adi, who was a PhD student of Shazreen Mohammed, started to just sort of take ownership of it. And so that's how the NOVA aspect of the program really took off. Yeah, I mean, a number of us are frequently looking at the GCN, you know, that's the high energy gamma ray alert from NASA, which also actually includes, of course, when the Virgo LIGO was operating, also the gravitational wave alerts, neutrino alerts, and so on. Most of us are signed up to the transient name server. We get ATEL notices. So it's really up to the individuals to say, look, there's something interesting, can we observe it? They contact me as the PI, and I usually take the responsibility of putting it into the queue, although others also can do that. It's not sort of, you know, I'm not the sort of single point failure if I happen to go on holiday, like when I went away to the Cedarburg in Easter where there's no electricity of any sort. So I put it in the hands of Steve Potter to look after it while I was gone. But the basic thing is that every afternoon about this time, I look through like the ATELs, I look through other notices, see if there's anything interesting. If there's something that looks interesting, I think might be interesting to others, I'll suggest it to them, and it just goes from there. So it is very ad hoc, it's very manual, and that's what we want to move away from, clearly.
Okay, thanks.
Hi, David. Thanks for an interesting talk. I have a question too. I wanted to ask, do you do any transient localization with SALT or MASTER? And
yes, we do. So MASTER is a perfect instrument to do, you know, to find an optical counterpart of something that has a poor position. For example, you know, as you're probably aware, the gravitational wave positions are not very good at the moment. And so you need wide field instruments to be able to cover the fields where these optical counterparts might happen. So MASTER actually was one of the first telescopes to make a major contribution, and it also was one of the ones that observed the GW 1708-17, as did many other telescopes. SALT is not so great if you don't know where something is. We do have an imaging camera, but the field of view is quite small. It's only 10 arc minutes. So we typically don't use SALT to go hunting for an optical counterpart. Rather, once an optical counterpart has been suggested, we then observe it by taking a spectrum typically to classify it. Yeah, so I hope that answers your question.
Yeah, it does. I guess I had another one that I wasn't sure if it's a good question or not, but I wanted to check.
Ask it.
So TDEs, are they detected as bursts or are they like a continuous detection?
No, they're actually quite slowly evolving things. I should have spent more time on some of those slides, perhaps. I can go back, but you know, they typically vary over time scales of about a month. So that's sort of good because it allows you to follow them up relatively easily. Whereas if they happened like a GRB, you know, most of the time you wouldn't be able to get onto it in time. But for these TDEs that we've been looking at, the light curves, yeah, I'm almost there. The light curves are quite slowly varying. So here's an example here. So this is rest days from maximum. So you can see here that this started to brighten. Well, this is even 100 days, you know, so quite slow stuff.
Okay. Yeah, no.
Well, those are the ones that have been found, of course. There may be other things that, you know, we're not sampling that frequently enough to know, to be honest. You know, there may be some observational selection effects going on. I don't know.
All right, thanks.
Okay, Damien, he said inspiration stuff. Thanks for the brilliant talk. I think Matt has a question. So if no one else.
If no one else has a question, I've got a question. Still on the I think it was the TDEs. I think you mentioned they were polarized at 2% or something like that.
Yeah, that's right.
Is that what's expected, and what's what?
Well, this is where I have to.
I don't know anything.
I have to plead total ignorance here. So this is the result. When we got the observation, which I sort of, you know, I was responsible for getting the observation, getting the data analyzed, and I sent it to, I'm trying to remember who it was now. Oh, it must have been the Polish group. They were quite excited because they said, oh, it's never been measured before. And that's, yeah, I haven't heard more about it actually. So I don't know, you know, it's just I have to plead ignorance on the topic. I'm really not sure what one would expect from a polarimetric signature. I guess it sort of depends on the geometry of the passage, how we're seeing it, but I don't know. It's not a topic that I'm familiar with.
Okay, fair enough. If there's no other questions, I do have another one as well, which was I think you mentioned your X-ray binaries. There was one that's highly obscured.
Yes.
Do you ever look at these things? Does that, you know, for like with ALMA or something like that? Is that a useful thing?
Oh, right, because of the dust and so on. Yes. Not me. I mean, my sort of wavelength domain of comfort is from optical through to UV and X-ray. I have very little experience in the infrared, and I have zero experience in the radio, although I'm now dipping my toe into MeerKAT in that sense, because we've actually observed a low mass X-ray binary as a DDT, which was an unusual one, which is called a transitional millisecond pulsar, where it flips between accreting and expelling material. And we detected it in a MeerKAT observation. But yeah, to answer your question, ALMA I've not used, and so I don't know, to be honest, what the observations that have been done with ALMA for these types of systems. What I can just say, though, is that I was gratified to hear that a proposal on JWST, which I'm on with many other people, led by Poshak Gandhi at Southampton, has just been approved to look at one of these transitioning X-ray binaries during an outburst. And obviously here it's the infrared, which is the major issue. So certainly it will be, the infrared is clearly an area where there can be observations of these systems that no doubt uncover different aspects, but that's not something that I'm personally experienced with. I should talk to Shazreen Mohammed actually, because she uses ALMA. Yeah.
Okay, cool.
Thanks, David, again for the brilliant talk.
Not at all. It was a pleasure. And as I say, if there's anyone in your department who's got an interest in transient things, yeah, don't hesitate to contact me. Yeah, I'd be happy to hear. You know, the more the merrier.
Well, hopefully there'll be some coming from Hyrax at some point, but yeah. I think you're
Right.
probably waiting for that.
Yes.
But yeah, we'll see. Yeah, cool.
Okay, thanks, David, again, and thanks everyone for